Example 3 is a little bit more complicated because it involves two loadings, F1 and F2. The F2 is added at the centroid of the cross section of the column. Right? The F1 is not. F1 has a distance of A plus half of the thickness, right, to the centroid. And determine the magnitude of the normal stress produced at point H and K. Again, they're just one positive, another negative due to bending. Right? You also need to consider the normal stress from the axial loading. Okay, the first step, we can use free body diagram to determine the F and M, but I will skip it. If you cannot tell this F and M directly, you try to use free body diagram. Okay, so here, based on our principles, here's the F. The equivalent F should be negative F1 minus F2. Right, so this will be negative 20,000 pounds. Right, so it's a compressive force. Then to determine the M, we need to know the E. Right, so the E for F2, the E is 0. Right, so the E for F1 is just A plus half of the thickness, half of H in this case. Right, it's a 12 plus 8 over 2. That is 16 inch. Right, so the M will be, again, F2 will not make any bending moment because it's just directly added on the centroid. So the M equals F1 times E. Right, so that is 8,000 times 16. That is 128,000 pound inch. And the second step, we determine the section properties, where the A is just BH, right? B4, H8, that is 32 square inch. And the I will be BH cube or HB cube over 12. It will be BH cube over 12. 4 times 8 cube over 12 equals 170.7 inch to the fourth. Okay, again, this is perhaps a little bit confusing. I need to be clear why this is a BH cube, not HB cube, right? Because the bending moment is added about this y-axis, not x-axis. Okay, the third step, we can calculate the normal stresses, the two components. The first one, component 1, will be this F over A, right? It's negative 20,000 over 32. So we got negative 625 psi. And the second component will be positive or negative MC over I. That will be positive or negative 3,000 psi. Just on which side is compressive, on which side is tension, is tensile. Okay, the bending moment is in this way. So at point H, right, this section will tend to be bended in this way, right? So on point H, it will be in compression. On point K, it will be in tension. Okay, here we can combine them together. Okay, so at point H, sigma 2 at point H, it will be in compression. So this is a negative 3000 psi. And at point K, it will be in tension. This is positive 3000 psi. Alright, so the last step, we can calculate that at the point H. It's just sigma 1 is negative 625 minus 3000. It will be negative 3625 psi. And at the point K, negative 625 plus 3000. This will be 2375 psi. Okay, so in some cases, you may also need to calculate the location to find the location where the stress is zero. Right? So, how to determine that point? We just draw the distribution. Right? So on the cross section, you have a distribution at the left end. It is negative 3. Negative 3,625, and on the right end, you have 2,375. Right, so here, this is the location where you have zero stress. Right, so if you want to determine the location, you can calculate the x here. Okay, so obviously here you have two similar triangles. Okay, in these two similar triangles, you can get a equation that is 3625 over x equals 2375 over h minus x. Okay, so from this equation you can solve the x. Okay, of course, this equation, this similar triangles, and this equation is obtained based on our assumption of a flat plane. Okay, the linear distribution of stress.